Ploss from Konstanz, and I would please share your screen, and we are curious to listen to your talk. It should work, hopefully.
Yeah.
Yes, okay.
You can see it, wonderful. Okay. Okay, can I begin?
Yes, please.
Okay, then. Thank you for this nice introduction, and I want to say welcome from the Lake of Constance. And, whoa, we're a little bit too soon. This project is a joint work with Robert Denk and Markus Kunze. And now let's take a look at the set of equations that we've just already seen. Okay, so here we once again at the first line have the biharmonic equation, just as in the last talk. And then in the third line, we have some Neumann boundary conditions and some initial conditions. But what makes this system so special is the second line, where we have the so-called Wentzell's boundary conditions, which allow the operator itself to appear on the boundary. And well, what also makes this a little bit special is that we consider this type of boundary conditions on Lipschitz domains as well, so we don't have that much regularity. Another way to put this Wentzell's boundary condition is to, let's say, insert the second line, the first line into the second line. So we can also see this as dynamic boundary conditions. And we will also do this if we later consider this as a Cauchy problem. But for now, let's go back to the original version, and that the operator itself appears on the boundary brings with it several regularity issues. For example, if one would just think to apply some regular Hilbert space theory or semigroup theory, then one would probably just demand that the Bi-Laplacian here lies in the space L2. But then, unfortunately, if we just consider the second line, this wouldn't make any sense anymore because we could not evaluate this operator on the boundary due to lack of regularity. So we need some special approach for this. And the main idea that is also used in the literature is to decouple the system into some part that just lives on the interior and some part that lives on the boundary. Before I go into details, I would like to give some background about what has been done before on these conditions. Of course, there are many more papers, but I would just like to point out a few. Much has been done for Wentzell boundary conditions for second order operators and just the Laplacian. The smooth case working on C-infinity domains and the space of continuous functions was introduced in a paper by Engel and Franielli from 2005. And what's a little bit closer to what we are doing is, well, there are 4 methods have been applied for Lipschitz domain for the Laplacian in a paper of 2003 by Arendt, Metafune, Pallara, and Romanelli, where they showed using Berling-Denis criteria that there is some holomorphy on the LP scale. And then later this approach was generalized by Nitka and Varma. And for example, they also obtained Hölder continuous solutions. On fourth order operators, much less is known. For Wentzell's boundary conditions, there are some first investigations in a paper by Favini, Goldstein, and Romanelli from 2008, where they considered the same system that we have investigated, but just on the space of test functions, and they showed that the operator is essentially self-adjoint. And now what are we going to do? We tried to, and we succeeded in using the methods from the second order case and to work them for the fourth order case. But there are several issues. One of the main challenges is that we cannot use any Berling-Denis criteria because fourth order operators, they don't have the necessary positivity property, just as was mentioned in the last talk, so we cannot use any LP theory. And what also makes this more complicated, if one uses form methods, one always wants to use integration by parts, which is easier for second order operator than for fourth order operators. So one needs some special versions of Green's formula. But first things first, I want to point out the decoupling idea. So we introduce a decoupled Hilbert space. We take L2 in the interior and L2 on the boundary. And here we have our system once again, this time in the dynamic version. And now we just split up the U as a U1 that lives in the interior and some U2 that lives on the boundary. And so we just see we obtain a Cauchy problem that lives on the product space. And so we obtain some additional initial value. And now one can already read off the operator that is connected to our system. This is just the Bi-Laplacian in the first component, and then the operator minus d nu delta here. And now one has to put some kind of coupling condition into the domain of the operator, just to ensure that in the end we solve the system that we originally want to consider. But what is very interesting, we do not have to put these coupling conditions into the initial conditions, which allows us to solve more general systems. So, for example, if one thinks of a physical way of seeing things, Wentzell's boundary conditions always mean that there is some energy that goes from the boundary into the inside or leaves the inside. And now one could think of the following example. We are in 1 dimensions and we are on the interval 0, 1. And one could consider the following initial value. We are completely 0 in the interior, but we are 1 on the boundary. And now if one wouldn't decouple, this would just be equal to the function 0. And if one would throw evolution theory, this would stay 0. But now one can see that if we do some semigroup theory, which we were all going to do later in some more detail, we will obtain some holomorphic semigroup, and then for solutions, we instantly get the coupling back because we map into the domain of the operator. And when we have some solution like this, and one can see rather nicely that the energy that just lives on the boundary goes into the inside of the system. And even more importantly, this also does not converge to 0 in the end, but it goes to some constant, as we will see later, but this constant will not be 0. So it is really each choice of points on the boundary gives another solution. Okay, but now we will go a little bit more into the details, and we are going to use form theory to obtain our semigroup theory for this operator. So we are going to use the following form, which shouldn't be a big surprise. We want to obtain a form for the Bi-Laplacian, so we just take 2 Laplacians here. We don't have a term that lives on the boundary in this simple version of the system, but we will see that via the identification of the operator, the boundary will come back into play. And we define the form on the following domain. U in the ground space, then the coupling condition that I mentioned, and then we integrate the Neumann boundary conditions just by needing that U1 lies in the domain of the Neumann Laplacians, which has also the advantage, as the Neumann Laplacian is a closed operator, that this will yield a closed form. Now I spoke about the domain of the Neumann Laplacian. I want to recall that this is not H2 as in the smooth case, but has some weaker regularity. More precisely, it is the fractional order Sobolev space H3 ½ with the additional thing that the Laplacian lies also in L2. And we will use this notation of the fractional order Sobolev space where the Laplacian also lies in L2. And now one can just calculate that A is a real, densely defined, accretive, symmetric, and closed form. And then by form theory, one obtains that there is some associated operator which is self-adjoint, and the negative operator generates a very nice semigroup. But unfortunately, we do not know yet whether this associated operator A really is the operator matrix A we saw from some slides before. So we need to verify that those two operators coincide, and this is somehow where the real work begins. So let's take a closer look. What does it mean that U lies in the domain of the abstract associated operators and AU equals to F? And now I just recall this. U lies in the form domain, and then we find some F in the ground space such that for all V in the form domain, we have the following equality, just like if we think of the theorem of Lex-Milgram, for example. So the form has to be F with V in the inner product in the ground space H. And this is where suddenly the boundary reappears. So this is the defining equality. And now we want to identify the two components F1 and F2. For F1, this is rather simple as one directly sees that the test functions lie in the form domain. So if we plug in some test function, we just see that the second part vanishes. And then we just have the weak definition of the Bi-Laplacian. So we directly obtain F1 is the Bi-Laplacian as we wanted. And now we want to identify the second component. And for this, we have to work a little bit more. Just to write things more nicely, we write W1 for delta U1. And then we obtain the condition W1 and delta W1 both lie in L2. Or as one could say in the notation from before, W1 lies in the Sobolev space H0 delta. And then of the describing an equality, the following remains. There is some F2 that lives on the boundary, such that for all V in the form, we have this one. And now one sees this reminds us a little bit of second Green's formula. And one would just like to throw the Laplacian over there and then identify F2 as some Neumann trace. But unfortunately, we are lacking regularity. So if V1 and W1 would lie in H2, then everything would be nice and we could do whatever we want. But as just mentioned, W1 only lies in the very weak space H0 delta. V1 is a little bit better, at least it lies in the domain of the Neumann Laplacian, so it has Sobolev regularity 3/2. And also the Neumann trace is 0, and this somehow saves us, because there is some asymmetric version of Green's formula, and we found the necessary theory in a book from last year by Bernd, Hasse, and Desnaux, using theory of so-called boundary triples and generalized traces. And if one applies this theory, one can deduce the following version of Green's formula. If U lies in the space H0 delta, and there is some G that already lies in L2 on the boundary, such that for all V in the domain of the Neumann Laplacian, we have this version of Green's formula, then U already suddenly has better regularity, and U and G is the Neumann trace of U. Moreover, this theorem also states that the space H3½ delta is just the pre-image under the Neumann trace of the space L2 gamma. So this is just the limit regularity for the Neumann trace. And now everything somehow perfectly fits together, because we can just choose F2 as our G, and then we can identify our second component. Don't be confused by the minus sign. This is just due to the fact that those two terms are just switched. And so one can identify F2 as the negative Neumann trace of W1. And so this is just the operator we wanted. So all in all, we have shown the following theorem. The associated operator to our form A is indeed given by this operator matrix A. and we can fully characterize the domain. So we have U in the ground space, we have the coupling condition here, then we have the Neumann boundary condition, and together with this one, this just means that U1 lies in the domain of the Neumann Laplacian. And we also here have the regularity we just showed on the last slide. Hence, we know that A equals script A, and so it is self-adjoint, and minus A generates this semigroup, which is real, holomorphic, strongly continuous, contractive, and so on, and it solves our system. In order to retrieve the Wentzell boundary conditions, one needs to think a little bit more, but we can use that holomorphic semigroups map into the domain, or even arbitrary powers of the domain. So the coupling condition not only holds true for U, but also for A of U. And then this is just the Wentzell boundary condition. Okay, so this is the first big result of this paper. And now we come to the second result, which is Hölder regularity of the solution, which is also known for the second order case. And it was shown there using some Sobolev estimates and some LP estimates. And precisely, we showed the following. If U lies in the infinite intersection of powers of the domain, then U1 is Hölder continuous. And by the coupling condition, of course, we even obtain that the U1 and U2 is just Hölder continuous on omega bar for some Hölder exponent. And now one might expect this behavior in low dimensions at least, because by Sobolev embedding, it is known that the space H3 half delta is embedded into the space of Hölder continuous functions. Now, H3 half delta, we have this regularity already in the form domain. So now one might hope, because we have much more regularity, that this exponent 3/2 might increase, and then this should also hold in higher dimensions. This is unfortunately wrong. So it is known that because Lipschitz domain is a rather rough boundary, though we are in the dA infinity, we don't have to have any better Sobolev regularity than 3/2. And so one cannot improve regularity this way. And there is some nice example to see this. It is a modification of a regularity counter example for the Dirichlet Laplacian, so second order case. One can think of the following domain even in R2, if we're identified with a space of complex number. One might imagine it as some kind of pi where we just ate 1/4 out, and then we can consider the following function. We take z to the power 2/3 and take its real part, then this is a harmonic function, but it does not lie in the space, as in any better space than 3/2, because of integrability issues in the origin. This does not yet satisfy the Neumann boundary conditions, so one has to adapt this example a little bit. You cut out the interior, and then you just apply the Laplacian and solve the Neumann problem and so on. But it is possible to adapt this example as a counterexample, and because it is harmonic, it will lie into d of a infinity, because the Laplacian is just 0, and we still have this issue with the Sobolev exponent. So unfortunately, we cannot increase the Sobolev index to obtain Hölder continuity, but there is another way to obtain Hölder continuity, and this is by increasing the integrability index P. Now, as I just mentioned, unfortunately, we don't know anything, at least yet, about LP theory. But there is some way to circumvent this, because if U is in the domain of A infinity, then suddenly the system decouples into two second-order systems, which just become a homogeneous and an inhomogeneous Neumann problem. So if U lies in dA infinity, we just can rewrite the system like this. Here we just have the Neumann boundary condition. Then again, we somehow introduce this W1 to write things more nicely. And then this is just this one. And of course, for inhomogeneous Neumann problems, LP estimates are known. And we found the precise estimates that we used in a paper by Nitka from 2010. And if U in H1 weakly solves the inhomogeneous Neumann problem, for F and G in some LP space with integrability large enough, I think the dimension D should be enough, then U is Hölder continuous as well. And now one can see this as an LR naught L infinity estimate, because of course Hölder continuous functions are also bounded. And one also can obtain an L2 estimate simply by integration by parts. And then one uses some interpolation. So if F and G lie in any LR space, then the solution to this Neumann problem has better integrability. And now one just reapplies those Neumann systems and so on. And soon we will reach the threshold R0. And so we will obtain Hölder continuity. So for any fixed dimension, we can find a K such that the kth power of the domain lies in the space of Hölder continuous function. So solutions are Hölder continuous, which is a nice result for itself. But it also allows, if we think of the Wentzell boundary conditions, for a point-wise evaluation of the Wentzell boundary condition. Okay, so finally, some further results, which I just want to go over rather shortly. In fact, we studied a little operator that was a little bit more general than mentioned in this talk. We had some parameters, alpha, beta, gamma, and we also had some extra term at the boundary condition. And for this just works the same. Then what we also showed is that the operator A has compact resolvent and discrete spectrum. So one can apply just a regular theory to obtain results concerning the asymptotic behavior. So one just gets the following. If we have some initial datum U0, then the solution will converge to the mean value taken in H, and the convergence rate is just the second eigenvalue, simply due to the fact that we have that only the constants lie in the kernel of the operator and 0 is an eigenvalue. And doing this calculation, one can just see rather easily that if we think back of the example from the beginning on the interval 0, 1, we obtain the constant 2/3. Then finally, what we also showed, it was mentioned in the last talk and will also be mentioned in the next talk, is that though we are not positive, we can also investigate eventual positivity, and we could also verify the property of this eventual positivity for our system. So if we start with some non-negative initial datum, we might lose positivity for some time, but we will get it back after a predictable time. Okay, so I'm coming to an end. So thank you very much for your attention, and just feel free to ask some questions. Thank you.
Thank you very much, David. Are there any questions?
So I have a question.
Yeah, Jochen.
Namely, maybe you mentioned it and I just missed it. So what happens if you replace the Laplace operator? So you have the square of the Laplace operator. What if you take the square of an elliptic operator with more general coefficients?
Well, currently we didn't fully investigate that case, but the theory itself remains applicable. But there are some we are not yet quite sure if all versions of the estimates we used are also applicable to that case, but we are rather optimistic that for some regularity demands for the coefficients, we don't know yet which ones, this should work the same.
Thanks.
Thank you. Any further questions, comments? Okay, that doesn't seem...
One more.
Yeah, Jochen, okay.
You mentioned at the beginning that you cannot do LP theory for this problem due to the lack of positivity. Now, if I get this correct, you have a semigroup which smooths L2 into L infinity, right? So shouldn't it be possible to at least obtain a semigroup on LP for P between 2 and infinity by interpolation?
Unfortunately, we do not obtain a semigroup on LP, on L infinity yet, because we do know that it maps into there, but we don't get a semigroup. We don't have any some kind of invariance argument yet.
So, but if the semigroup maps L2 into L infinity, then L infinity is invariant, right? Because it's smaller than L2. So in particular, L infinity is mapped into L infinity.
Maybe I can comment briefly. I mean, you don't have a boundedness on L infinity. I mean,
okay, so at time zero. Okay, so you get a semigroup property, but okay. Yes.
It just lands. It just lands in the space, but we don't have any continuity. Yeah, that was it.
Thank you.
Okay. Now, any further questions? Jochen, you are done? Okay. Okay, then let's thank David again, and we continue in about 9 minutes.
Schön, was ihr da habt. Schön. Ja. Wie lange bist du jetzt eigentlich bei Robert schon, David?
Jetzt seit 2,5 Jahren.
Oh, warte mal, ich merke, das wird hier noch aufgezeichnet. Ich glaube, vielleicht lassen wir den privaten Plausch.
Ja, ich glaube, die zeichnen alles auf, aber veröffentlichen am Ende nur den Teil, der zu den Talks selber gehört. Aber,
okay.
Ja.
Okay, dann vielleicht doch jetzt. Seit 2 Jahren oder 2,5 Jahren?
Ja, 2,5 Jahren. Also im Oktober sind es dann 3 Jahre, aber ich denke, dass jetzt während Corona und allem, da wird es noch ein bisschen länger gehen. So.
Ja. Ja, wie geht's dem Robert? Den habe ich schon länger nicht mehr getroffen.
Ja, auch ganz gut, genau. Ja. Ich glaube, er hat ist für die Konferenz irgendwie nicht registriert, weil er noch irgendwie andere Sachen zu tun hat. Und jetzt kommt er irgendwie nicht rein ohne das Passwort oder irgendwie so.
Gut.
Ja, ja.
Ja. Schön. Haben wir uns eigentlich schon mal live gesehen irgendwann? Ja.
Wahrscheinlich in einem Oberseminar in Konstanz.
Das kann sein.
Oder vielleicht bestimmt mal auf einer Tulka, oder?
Ja, wahrscheinlich nicht mehr, als du schon da warst.
Also ich war erst 2-3 Mal oder so auf der Tulka, aber
ich glaube, Markus hat mich mal nach Konstanz eingeladen, das stimmt. 2019 war es.
Irgendwas war mal, ich glaube schon.
Ja, schön.
Ja, das mit den generellen Operatoren zweiter Ordnung ist schon irgendwie interessant, weil wir doch irgendwie brauchen so viele Bausteine, die wir da benutzt haben. Und irgendwie sind dann manche nur so formuliert, sollten aber eigentlich schon irgendwie tun. Man muss das mal noch irgendwie genauer anschauen, aber ich denke, da sollte man das retten können.
Ich meine, das ist merkwürdig, weil die sich doch irgendwie ganz komisch verhalten, ja.
Naja, das ist, man läuft immer diesem 1,5 Regularität irgendwie hinterher.
Ja. Geht es jetzt weiter um 25?
Mein zweiter Monitor ist gerade leider während des Vortrags ausgefallen.
Ja, 25.
Ja.
25 geht's weiter.
Ich glaube, dann esse ich jetzt noch schnell was, ansonsten sinkt die Laune. Bis gleich.
Gleich.